Thank you for joining us in the beautiful Ardita Social Hall. So the program for this morning, we're going to try our best to present some scientific and astronomical ideas of the solar eclipse from Mr. Bill Kafig. He prepared a beautiful PowerPoint to highlight some of the main features of what we will be experiencing in just a few short weeks, and then followed by a talk by me trying to cover some of the halacha and hashkafic ideas behind the eclipse. I will be giving out handouts. The handouts are just meant to help those people who like to look at the sources while I'm talking. It's not necessary to use the handout. Most of it is Hebrew sources. Last night when I finished preparing them at about 12 o'clock, the art scroll offices were closed, so they couldn't translate it for me. But it's a guide for those who want to use it. For those who don't want to use it, don't feel that it's necessary. You can hopefully gain a lot even without having all the sources understood in front of you. And without further ado, I'd like to ask people to get going.
All right, you want me to get going? I'm done. Okay, you've all probably heard about this wonderful thing that's going to happen in about 6 weeks from now. So I've been asked/drafted to tell you probably more than you ever wanted to know about eclipses. The nice thing about this is there's also some wonderful vocabulary for those of you who are working on getting ready for your ACTs or like to play Scrabble. It will also help you there as well. So let's start out. Hey, the eclipse, it's begun! Oh, okay. So, very simply, what's an eclipse? An eclipse is simply when one object comes in front of another and blocks it. Yeah, or something like that. So we have a couple of different flavors of eclipses. We have something called a partial eclipse. So this happens, and I'll see if I can start using some of my additional audio-visual aids. So this will happen when an object comes in front, but not quite all the way in front of the object. So we call this a partial eclipse. Now the eclipse that we're going to be seeing in about 6 weeks will also begin with a partial eclipse as the moon moves in front of the sun. Then, as it comes right in front of the sun, we have something that we can call an annular eclipse, which means that the moon is centered in front of the sun, but there's still a lot of light coming around. And we'll get into why that might happen. There's also something called a total eclipse, when all we'll see is the solar corona around the ridges of the moon. Then as the moon continues to move, it's going to go through another partial thing. Ignore the giant alien figures holding onto the moon, but all right. So that's the fundamentals of the eclipse. But the eclipse is really all about shadows. So here's where we get to practice our Scrabble terminology. In order to get a really good eclipse, everything has to be in proper alignment. We give that a special word called syzygy. Has nothing to do with scissors. Syzygy. And that simply means everything is aligned properly. So in terms of shadows, we have the umbra. And in fact, this was working kind of well, so we'll go back to this. So, let's see. Do you see how the moon over here, the moon tennis ball, is not exactly covering or not really entering this bright part of the sun, but again it's still casting some sort of shadow. It's sort of a half shadow, so we call that the penumbra. And when I put my hands free again, I'll show you where that comes from. That actual nice dark spot that you see right there is the umbra, and then the antumbra is a funny mathematical thing that happens on the other side of the moon. So over here, the sun is really wide, at least this big. Or as the one-armed man said, at least this big. All right. So So you're going to get light from all parts of the sun. You're going to get it from the far, in this diagram, the top side, the bottom side, the left side, the right side. And that's going to trace a line which is going to come and cross an object. In this case, it might as well be the moon, since that's what we're mostly talking about. And where the moon completely obscures the light from all parts of the sun, it makes that very dark shadow here called the umbra. But yet there's still light that's coming from here and is only partially blocked because, again, the sun is so large, and it makes sort of a half-shadow type of deal. We call that the penumbra. If you go far enough away, there's something here called an antumbra, which again is that very dark spot, but this usually happens much further away. And we have up here in this top diagram, sorry, lots and lots of pictures I find often help quite a bit, is that if the alignment isn't quite right and the moon is far enough away, the umbra actually ends out here in space, and the antumbra is actually what comes in contact with the Earth. We're going to be very lucky, and we're actually going to be in the front part, before that crossover point over here, and that's actually going to put us in the umbra itself. Okay, enough of it. One of those wonderful things I forgot about. Never look directly into the sun, never look directly into the projector. Okay, so let's talk about orbits. And that's...
People just couldn't see the screen. So.
I'll put it there because then you're going to get a really good view of the globe. So rarely are orbits perfectly circular. So we like to think that, I'm just going to hold this so that it's north-south correlates with up and down. So we like to think, very simplistically, that the moon circles the Earth on this nice flat plane over here. And, but unfortunately, it doesn't really do that. It actually swings out further at one point, and again, we're going to get to some more vocabulary words. So the furthest point out here that we're going to get to is called the apogee. And the important thing from where we're sitting here is that the moon is going to appear smaller. And we see this a lot of times when, at either moonrise or just before dawn, when you look at the moon and it's sitting there on the horizon and it looks crazy huge, right? I think what they call it, an autumn moon. There are a couple of things. There's certainly atmospheric conditions that lead to part of that being an illusion. And part of it is actually that the moon is, as it returns on its part of its orbit over here, where it's much closer to the Earth, and it really does appear larger. In fact, it will appear about 12% larger in its closest point as opposed to its furthest point. Just for scale, assuming that this is a 1-foot globe, this tennis ball is actually about the right size for this particular model, except this is about where the International Space Station orbits. If I throw this to the Alan, all the way back there, I did shower this morning, Alan. Could have said, all right. If I throw it all the way back there, about 30 feet away, that's about how far in this scale the moon is from the Earth. That represents about 250,000 miles. The difference between where Alan's sitting, which is the average distance, and at the moon at its furthest point would be another 6 feet behind him. I'm sorry, another 6 inches behind him, or another 6 inches closer to us. So that there is a definite wobble in the moon's orbit. And again, at its closest point, it's going to appear to be about 12% larger than at its furthest point. Let's see, what else we need to know about this. Okay, so we've added one level of complexity. Orbits are not perfectly circular. They're elliptical. And not only are they elliptical, they're not planar, which means that anything that happens on a flat surface is planar. So if the Earth is sitting like this, the moon does move around the Earth like this, does move around like this, but it's not planar to the sun. That is to say that the moon is actually moving, let's find our sun. Okay, so if this is the sun, the moon is actually orbiting the Earth at a slant. And we see that. Can you see that in this one? No, I had that on another drawing. So the moon is actually orbiting at a slant. Because if everything were flat and on a plane, we'd be seeing these wonderful solar eclipses, lunar eclipses, and all sorts of stuff like, every month. But only if you're on the equator. So Earth going around the sun, moon going around the Earth, and just because that's not complex enough, the Earth wobbles. Which is why we see these globes. How many people have wondered why we don't see globes like this? Why are they always sort of laying on the side? Because the axis rotates. And not only does it rotate, it rocks back and forth, which gives us our seasons. So depending upon where the moon is in its non-planar orbit around the sun, well, moon orbiting the Earth, but that plane is not on the same plane as the Earth and Sun is, plus the Earth wobbling back and forth, sort of starts making these occasions of eclipses a less common event. So now we can go ahead and front row scene. They shouldn't be too penalized. All right. So does the moon's location in its orbit make any difference? Yes, absolutely. We were just talking about that. So we over here at its perigee, that is to say that at its closest point to the Earth, it occupies about 34 arc minutes. All right, what's an arc minute? And who cares, right? So if you go outside and you want to get a rough idea of where something is in the sky, you hold your hand out arm's length and you put the bottom of your hand on the horizon. The top of your hand represents about 10 degrees up from the 10 degrees up from the horizon. And you can do that. There's 20 and 30, and of course there's a little dance. And all right, but no, 20, 30, and all the way up to about 90 degrees. So that's one quick way to approximate the elevation of an object, is just by holding your hand out and counting up. Which means that each one of your fingers is a little bit more than 2 degrees. So 1 degree is roughly half a finger width. So this 34 arc minutes is a third of that. So we know that 1 degree, take a circle, you divide it up into 360 equal parts, and each one of those parts you can subdivide into 60 sections. We call that an arc minute. And those can, of course, be divided further into arc seconds, which is, again, only 1/60th of that. So in the orbital position, when the moon is closer to the Earth, it occupies more space. And we still have the sun out here. Back to our model, if the sun would need to be, you know where the Home Depot is, about 2-point-something miles from here up on page and 170. That's where the sun would be, just in terms of this model. So we've got the sun over here, and depending upon where in the annual cycle we are, where the Earth itself is going to be closer to the sun, which makes the sun look bigger, or if in our case, summer, it's actually the Earth is further from the sun in the northern hemisphere. So the sun is going to appear smaller. In our case, we're actually going to be very, very close to the perigee over here, where the moon appears larger, which is the right set of conditions that will get us to a total eclipse. All right. So, we love talking about coincidences. It just happens to be that the sun is about 400 times wider than the moon. just happens to be that the moon is 400 times closer to the Earth than the sun is, which means that from our perspective, the sun and the moon are about the same size. And this is a very interesting thing because it allows us to get these really wonderful eclipses. Otherwise, if the moon were either further away, or the sun were larger, or the moon were smaller, as it is in so many places throughout our solar system, yeah, the moon would be a little dot going across the face of the sun, and everyone would go, yeah, okay, that was exciting. But it's not. For us, we've got this wonderful total eclipse coming along. So when the situation, the situation is correct that we're further from the sun, making the sun look a little bit smaller, and the moon is at its closest point to the Earth, which makes the moon look bigger, we get the perfect eclipse. Just because we're talking about eclipses, we have something called the lunar eclipse. This actually happens fairly frequently. Every time the moon dips behind the Earth, it falls into the Earth's shadow. Again, because of the angle that the moon is rotating on, many times the moon will be outside of the Earth's shadow, so we don't get it, but oftentimes, certainly much more frequently than we see a solar eclipse, we'll have a lunar eclipse. But again, this isn't too terribly exciting, so let's move on to more exciting stuff. The solar eclipse. So, we're talking sun really, really huge, sitting up near the Home Depot, and that's going to be, oh, I have it written down here somewhere. Sorry, don't worry with the light. There we go. Okay. So the sun would be about 202 feet across, 2/3 the size of a football field, sitting at Home Depot, just so we get our sizes right. Which means that, you know, it's not huge, and the moon isn't huge. So what winds up happening is the focus point of the umbra actually only traces out a fairly narrow path on the surface of the Earth. It's about 100 miles wide. So the penumbra, the not quite as dark area, is going to try to cover a much wider area, and depending upon where the shadow hits the Earth is also going to determine how large or how small it's going to be. I'm going to move along just because I know I'm running out of time. So, is it rare? This is a nice little chart covering 20 years of where there are either complete or partial solar eclipses as they trace across the Earth. This is the one that we're going to see right here, and that's coming up. So roughly once every 18 months, somewhere on the planet, there's going to be a solar eclipse. Now, I have this cool video that I would like to show you. It is put out, I believe, by NASA and is available on YouTube. And it lasts about as long as the eclipse
does. What we're talking about is several visualizations of the path of the moon's shadow.
That's going to make it a lot less exciting. Let's see. Okay, computer, do what I want you to do. Ta-da! Okay.
The eclipse in 2017, everything in it is driven by the data. So the color of the ground, the position of the path of totality, the lighting from the sun angle, all of those are things that are based on data. A lot of NASA products are used to create this visualization. I used the Lunar Reconnaissance Orbiter, the laser altimetry data from that, which gives us a digital map of the elevations on the moon. For the Earth, I used something called SRTM. This was a radar that was flown on the space shuttle. For the positions of the Earth, the moon, and the sun, I used a JPL ephemeris. Ephemeris is just the list of positions, but it's the most it's the most accurate tabulation of those positions. This visualization is unique because it shows the effect of both the irregular edge of the moon, the limb of the moon we call it, and the elevation of the observer. Now, we've known for a long time that the elevation of the observer affects where the shadow is. We've also known that the mountains and valleys along the edge of the moon affect the shadow. So you may have seen on eclipse maps in the past that the image of the umbra, that shape of the shadow of the moon, is drawn as a smooth oval.
This is the pen
we know
umbra.
that the moon isn't smooth. Around the edge of the moon, we have these sort of jagged peaks and valleys. And a peak can block the sun a little bit earlier than you thought, and a valley can let the sun in a few seconds longer than you thought. The combined effect of these peaks and valleys is to create a shape that's not really an oval, it's more like a polygon. But it hasn't actually been seen in exactly this way before, where we calculate those circumstances for every point on the map and draw that shape. Totality is that 2 minutes or 2.5 minutes when the moon completely covers the sun. The sudden darkness of totality is just something that a lot of people can't compare to anything else. I love the idea that I'm giving this kind of map to other people, and especially that it's more detailed and more accurate so that people are actually in the right place to see it.
Okay, so that was a wonderful little video. Again, that video lasted about as long as the actual eclipse will last. So now let's just get into the actual viewing. So again, safety is going to be a very good idea. It's never a good idea to look at the sun with the naked eyes. At least put a jacket on me. You can see us. You can purchase these what they call eclipse glasses. I have a little bit of the material. It's a mylar aluminized piece of plastic, and it lets through about 1/1000th of 1% of light. So I've got about 1,000 lumen flashlight over here, and if you click it on, you can just maybe see a little bit of light coming through it. So this is what's going to be needed. That is a 6" by 6" piece, which is going to go on my telescope. From Amazon, no, I don't get any kickbacks. You can purchase glasses, whether they're the cheap paper glasses, plastic glasses, covers for binoculars, covers for your telescope, and so forth. If you get them in bulk, they're about $1.70 each, so there's really no excuse not to have. This number is on the low side. It actually blocks about 99.99% of the damaging visible light and 100% of the UV. So where are all the cool kids going to be? Well, when you go online, there are a number of sources. One of the best is eclipse2017.org, and you can click on the map and it will give you a little table of where the eclipse is going to be, how much in the path it's going to be, etc., etc. There is one thing I really, really want to caution you about, and that is that the time is marked UT. This is Universal Time, which is kind of the newfangled time for Greenwich Mean Time. We're 6 hours off of that. So when you see something over here that says, oh, the start of the partial eclipse is going to be at 14:49, that doesn't mean 2 o'clock. That means something more like 10 o'clock. So please be aware and that you have to do your own computations to figure out, basically subtract off 6 hours from the time that it shows here. Otherwise, you're going to have to wait another 160 years before you get this opportunity again. So where to go in order to see this? I read just this morning that the Missouri Botanical Gardens are expecting to have about 20 seconds of total eclipse there. Chesterfield is, just into this range over here. I personally like a spot. It's going to be down a little bit here on 44. It's not going to be at the path of greatest totality, but I should, anyone who heads out there is going to get probably close to 2 minutes of it. St. Peter's is also highly recommended for viewing. Again, please check the eclipse.2017.org.
I just saw in the spot for this week that Rabbi Heber is going to be taking a group to, they're going to fly into Kansas City and go to St. Joseph's. And so they're going to start on Sunday and goes through Monday. They're going to do it together. So I guess, if anybody would be interested, it's all kosher, Star K.
Star K?
Yeah.
All right. And that, I guess, wraps my part up.